like to welcome Bobby Buss, who's applied to join us. Bobby has worked for, I don't know, 50 odd years at IRTF in Hawaii. Uh,
It feels like it.
one of our noted asteroid astronomers in the community has a whole taxonomic scheme named after him, and has been very generous in being the discoverer that's named a bunch of asteroids for PSI people. So, Bobby, welcome, and I'll turn it over to you.
Great. Thanks, Mark. Um, so let's see. I guess you guys can see the screen.
Yes.
Uh, okay, good, good. So yeah, just a little bit of background. I mean, I know a lot of you already, but yeah, Mark was half right. I was actually in Hawaii at the IRTF for 23 years. But it seemed like 50 towards the end. Um, But yeah, I've sort of moved around a little bit. Did my undergraduate work at Caltech. From there, worked at JPL for a little while, and then Lowell Observatory in Flagstaff, and then finally got the bug to move on to grad school. Went to MIT to work with Rick Binzel, and then moved to Hawaii. And so I've reached that age where retirement sounded good, so I jumped for it. So let's go ahead and get started here. What I wanted to do today was just to tell you a little bit about the IRTF. It's been in operation for 45 years, and so I was there for about half of its life. The picture that you see here is during a lunar eclipse. It was taken by Mike Connolly, who's one of the IRTF staff astronomers. And you'll see a few pictures of his through here. All the pretty ones are from him. So let's see. How do I move how do I switch screens
Switch screens or advance the slide?
or advance the slides? Yeah. Oh, I guess it's down. There we go. I found it, the magic button. Uh, so this is a shot out of Hilo Bay with one of the usual cruise ships, cargo ships, whatever it is, sort of floating through. And I show this just to give you an idea of what the view was generally like, not the bay, but the mountaintop, pretty much every morning in Hilo. I'd wake up to this. And you can see some white dots up there in the center. Those are some of the telescope domes on the East Ridge. Um, and every once in a while, during the day, the ground would shake a little bit, or you'd hear word of an eruption going on down south. And it brought to mind that I really was living on a volcano. And so the geology part of me, loved that. Um, it turns out that the ground that we were living on is about a 500,000 years old, and is part of the highest mountain in the Pacific Basin. Um, the second highest, Mauna Loa, is just to the south on the Big Island. And we used to tell visitors that measured from the base, if you went down to the ocean floor and measured upwards, the height was about 33,000 feet, which is a few thousand feet higher than Everest. So we used to be proud of living on the tallest mountain in the world. Now, Mauna Kea holds a lot of significance for both astronomers and for the indigenous peoples. The native Hawaiians find it a sacred cultural site. People went up there long ago to look for stones to make tools out of. They worshipped gods who live up there. Poliahu, the snow goddess, is probably the most famous one. She's the sister of Pele. So Pele lived down south in Kilauea. Uh, Mauna Kea is probably if not it is one of the best astronomical sites in the world. And what makes it that way is its isolation out in the middle of the ocean. The clouds that you see there in that picture, that band of clouds, is the marine layer. It flows out, drops and flows out to the ocean every night. And then in the daytime, as the ground warms, the clouds raise up. And usually in the afternoon, they actually cross the summit. But then again, at sunset, they will drop, leaving a very clear sky. Usually no high clouds. It turns out that the latitude for Maunakea at about +20 is in the subtropical zone. So we don't get a whole lot of high clouds except when storms come through. The high altitude is great for infrared astronomy, very little air, very little water vapor. And the ocean provides a very flat surface for the breezes to flow across. So when the winds, especially the westerlies, hit the side of the mountain, they flow right up along the side of the mountain and over without creating too much turbulence. So that leads to very good seeing, sometimes absolutely incredible seeing. And the Big Island is not very populated, so it's got nice dark skies. Here's a view of the top. Officially, 13 telescopes up there. If you count, you'll only count 12 actually in this picture. The VLBA dish is a couple miles away off on the left-hand side, down off of the summit. The telescopes that you normally hear about are marked here, the biggies, the Keck twins, 10 meters, and then there's the Subaru telescope, operated by the National Observatory of Japan, and the Gemini 8-meter North telescope. Then there's the intermediate siblings. UCURT off on the left there, CFHT, and the NASA IRTF. Now, it turns out that the IRTF and UCURT are both infrared telescopes, optimized for the infrared, and they were both constructed at the same time, leading people at the time to ask, well, why are you building two of these? I guess that there was money and interest, so it happened, and I'm glad that it did happen. Curiously, all three of these telescopes started operation in 1979, so they are very closely related. Now, the IRTF started actually in 1974 when NASA decided that it needed a mid-size, large-size IR telescope to help support planetary missions. And so a contract was set up with the University of Hawaii to build such a telescope. The immediate goal was the Mariner Jupiter-Saturn mission, MJS, which eventually got turned into the Voyager missions. The IRTF is a 3.2 meter telescope, very long focal length, but it has a 2.5 F ratio 2.5 primary. Here's one of those Easter eggs found out of the archives. This was actually at the dedication in 1979. Shows the size of the yoke. I should say that earlier picture was actually taken at the shipyard where the telescope was constructed, where the mounting and tube were constructed. But here it is in the dome. You can see the size of the yoke. It literally is built like a ship. If you run into it, you know it. But that stiff mount is actually really useful. It helps with keeping the telescope very stiff, allowing for accurate pointing and tracking. The one disadvantage with the English style yoke is that you can't go too far north. And so there actually is a declination limit for the telescope at plus 69. But the people at the time, the people at NASA headquarters didn't think that that was that big of a problem, since most of what they were interested in was along the ecliptic. And so anything up around plus 70 or higher, they didn't really think that that would be a problem. The IRTF, as I mentioned earlier, is optimized for the IR. The idea is to try to minimize the thermal emission that you measure from the telescope, the surroundings, the atmosphere. So one of the things that is, well, there's several oddities about an infrared telescope. Number one, usually that very large focal ratio. That leads to the ability to have a small secondary. Small secondary will radiate less heat. In this case, our secondary has, if you look at the picture there, right in the center of the mirror, is a little button. And that's a deflector. That's to try to keep light or radiation coming up from the Cassegrain hole where the instruments are mounted. So any heat being generated by the instruments would be deflected out and not reflected back down into the instrument. The IRTF does have chopping capabilities. It used to have very good chopping capabilities. The chopper has aged over time, and there is work right now to try to install a new chopping system. The IRTF has been funded, the operations and maintenance of the telescope have been funded by NASA for those 45 years. Currently, the funding is through the Near Earth Object Operations Program. And one of the key missions of IRTF is to characterize NEOs in support of NASA's planetary defense efforts. Now, this here is a little comparison. These are both images of Jupiter at 5 microns. The one on the left was taken not long after the IRTF opened with a single pixel array detector that would be scanned up and down the planet. And so you would then add all of the scans together and create an image. It took about an hour to make one of these scans. You can compare that to today's technology with our large IR arrays, where that same image can be obtained in less than a second. And as you can see, much better resolution than was possible back then. Here's another comparison over the years. If you look at the old picture that's up in the left and look at the bottom of the telescope down at the base of that orange tube, you'll see one tiny little instrument hanging off the bottom. So that's how that first image of Jupiter was taken, was with a box that was probably about the size of a toaster. Today, the IRTF looks a little different on the back end. All that blue structure, that rectangular area that's sort of blue, that sort of takes up the entire base, is a cooling system. Inside of those cabinets is housed all the electronics. Anything that would generate heat, the heat is pumped out, dumped outside. And then the instruments are down off the bottom. We have C-shell, or I-shell is the red instrument. It's the newest instrument that we have. And Specs and Mercy are also on there. Now, the plot, the pie charts that you see there, demonstrate how the observing technique has changed, or the observing focus has changed over the years. With advances in instrumentation, we have gone from primarily imaging and photometry back in the 1990s till today, where nearly everything that we do is spectroscopy. So just walking through the current instruments a little bit. SPECS is our workhorse. It's a low to medium resolution near IR spectrograph and imager. Uh, it was designed by the IRTF staff and built uh, by the IFA, the machine shop. Of course, all the lenses and electronics and stuff were outsourced, but the assembly of the instrument was completely in-house. It was commissioned in 2000 uh, due to advances in the array technology and computer capabilities. It was decided to upgrade the system in 2014. The instrument works basically the same, just better now after that upgrade. There are multiple spectrographic modes, ranging from a low resolution prism mode, which is used mainly for small body research, asteroids in particular, uh, to higher resolution modes, the SXD, LXD modes, which are used more for studies of molecular absorptions, emission in atmospheres and comets. SPECS also has a near IR slit viewing imager and guider. It is used both ways. In fact, the imager is used a lot for ongoing programs to monitor the atmosphere of Jupiter and the other planets. And then the guider mode is a slit viewing guider, so you actually see the target on the slit. Now, mounted on the side of SPECS is MORIS. It's an optical CCD system based on the Poet's design. It was built originally by MIT, Jim Elliott's group, and in fact, Amanda Sikafous was the lead on getting MORIS built for us for the telescope. The idea was to have a permanent rapid imaging system for occultations and transits at the IRTF. By mounting it on SPECS, though, it gave us a lot of flexibility to use it for other things. And so it turns out that MORIS is used an awful lot for guiding, and it has increased our guide accuracy and capabilities. We can observe much fainter targets now because of MORIS. iShell, as I mentioned, is our newest spectrograph. Again, designed and built in-house. Started operation in 2016. It has a resolution up to 75,000 in multiple bands, covering from J band through M, so basically 1 to 5 microns. It also has a near IR slit viewer, imager, and guider. Down in the lower right, you can see an example of the cross-dispersed spectrum. This is actually a calibration spectrum taken of the methane cell. Methane, there is one band where this cell works, and it is used for radio velocity measurements. So all the dark structure in there is embedded on the spectrum as wavelength calibration for the RV measurements. MERSI is an old instrument originally built at Boston University. It was a very standard mid-IR instrument array for that time. It was built kind of with the IRTF in mind. So it was brought out to the telescope first in 2002. It covered the range, or it covers the range from about 2 to 26 microns using various filters and low resolution grisms. But unfortunately, around 2009, 2010, MERSI started having more and more electronics issues. The Boston University group that had built the instrument had sort of disbanded. And so the IRTF inherited MERSI kind of as a unwanted stepchild. We took it over trying to keep it as healthy as we could, but finally in 2011, the array controller died, and so we had to shelve it. David Trilling from NAU was interested in reviving Mercy, mainly because mid-IR cameras are very hard to find these days. In fact, I believe that Mercy might be the only mid-IR camera for a ground-based telescope, certainly in the US. I think probably across the Northern Hemisphere. I believe that there are still a few working mid-IR cameras in the South. But with the space-based observations, the WISE mission, the upcoming W1 mission, astrophysicists generally don't feel that they have that much of a need for ground-based mid-IR observing. But it turns out for planetary purposes, it actually is quite important, mainly because things in the solar system are not static. Things orbit around the sun, changing positions. Things are happening all the time. And so you want the ground-based capability in order to do monitoring programs or studies of new phenomenon in the solar system. So that joint project to refurbish Mersey started in 2020. We replaced the helium and liquid nitrogen cryostats with a closed cycle cooler. This meant now that Mersey can be on the telescope all the time. Before, we would have to schedule very discrete runs where the instrument would be on for a week at a time. The cost of liquid helium in particular became very high, still is. And so it was just not financially worth keeping Mercy in that state. So with the new technologies in the closed cycle cooling systems, we found one that would work for us, keep Mercy down at liquid helium temperatures. We also upgraded the array controller and added a cold dichroic inside of the Dewar to send the visible light outside to another Andor camera, just like Morris. And so we call that camera now MOC, standing for the Mersey optical camera. And in 2022, it went onto the telescope in shared risk and is now regularly scheduled to anybody who wants to use it. The newest attachment to the IRTF is actually a finder scope. It's called Opihi. Opihi is Hawaiian for the little limpets that attach to rocks and stuff. So this is sort of a finder scope that attached itself to the side of the IRTF. It's a 17-inch plane wave telescope off the shelf. And again, we have another Andor camera, a 2K chip that we use for imaging. There's a set of Sloan filters there so that you can do filter photometry or imaging. It has a half-degree field of view, can reach down to 20th magnitude in about 1 minute. And the main reason that Opihi was suggested by the asteroid community was to help with near-Earth objects that are so newly discovered that the orbits and ephemerides are not well known. So if you know that a new discovery has been made that is bright enough that we would want to try to observe it with IRTF, but didn't know exactly where it was, you could use Opihi to find the object in real time, do a small correction to the ephemeris, and then allow the asteroid to be found in the smaller fields of view of specs and tracked on accurately. In the upper left, upper right, sorry, is one of the commissioning images taken of M65 and M66. This is about the only camera on the telescope that gives really pretty pictures. So besides being an asteroid finder and photometer, I figure it might be used for astrophotography as well every once in a while. One of the things that we're using it for, or starting to use it for, is monitoring sky transparency. So you can keep it running full time and use it as a sky monitor to look for clouds or changes in transparency during the night. That use is just starting. I can't say how it's working, but the hope is that we might be able to run it every night and keep track of what the cloud or transparency conditions are like in the direction that the IRTF is pointed. We also welcome visiting instruments to IRTF. This right here is an image of TEXES. We welcome anything that presents new technologies or helps expand the ranges of wavelength or resolution available to IRTF to invite new users and new science endeavors. The current list of instruments that we have, TEXES is on regularly. BASS is a small prism spectrograph, goes from 3 to 14 microns. It comes out every once in a while, and HIPWAC is sort of hit or miss. I think that the last time that HIPWAC was on the telescope was a couple years ago. It's a heterodyne spectrometer with a resolution of about 1 million. This plot shows telescope usage, sort of a breakdown of how the different science categories are how the different fields use the telescope. The division, that line in between, divides the solar system studies, sort of the reddish part of the pie chart, from the cooler colors down below, which are the astrophysics. That line generally is horizontal, representing the fact that 50% of the time is dedicated to solar system studies. Sometimes with daytime observing, which focuses on solar system objects, then the amount of time during a semester for solar system observations can actually be higher than 50%. The observing time is open through the proposal process to anyone worldwide. The telescope is classically scheduled with multiple programs per night. Most of the observing is carried out remotely. So that means that there's even more flexibility now in how we can schedule things. Sometimes 3, 4 programs in a night. That makes the scheduling of the telescope a process that happens every 6 months pretty daunting. I used to do that while I was at IRTF. Now somebody else is doing it. The daytime observing I mentioned, that is actually a unique feature for IRTF. So here's a picture. This is actually pretty common for IRTF to be open like this during the daytime. If you look down in the lower part of the tube, you can actually see the primary mirror reflecting the sky. The biggest trick for the telescope operators is to make sure that the sun doesn't fall onto the primary. That's something that would not be good. There are instances, marks around the dome, where every once in a while the sun did hit the primary, and it definitely does leave a mark. The plot shows the breakdown of daytime observing hours for about the last 10 years, showing where most of the time goes. A lot of it goes to Venus in support of the Akatsuki mission. I think I pronounced that correctly. But also comets come in. Whenever there's a bright daytime comet, uh, observing time will be given for that. And Jupiter is regularly observed as well. The instruments that are used in the daytime are primarily TEXES, the visiting instrument, and SPECS. Well, and actually now iShell for the comet observations. So basically, all of the instruments can be used in the daytime. Remote observing is literally from any place where you have a good internet connection. The picture up at the upper left is from JPL, a group working with Orton, and down below somebody's living room someplace. Um, the amount of remote observing has increased starting in about 2000, around 2000, 2001. In fact, the impetus for starting remote observing actually occurred on September 11th, 2001, when all flights to Hawaii were stopped. All flights everywhere were stopped for a while. People were scheduled on the telescope, didn't want to lose the time, and the internet was sufficiently robust at that time that we were able to export the control windows to a remote computer, and they were able to operate the instrument successfully. There was definitely a learning curve, but over time we got better and better at it, made it much more efficient in how we share the windows to observers. And so as you can see, between 2002 and 2016, roughly, there was a pretty constant rise in the amount that of remote observing that was used. And that was sort of a time period for observers to be accustomed to not going to the telescope, not actually being in the control room, sitting next to the telescope operator. If you look at that time plot, sort of around between 2000 and 2022, or sorry, 2020 and 2022, you'll see a flat black line up there. That was COVID, when we were 100% remote. Most of the time, when it dips below 100%, it's when visitor instruments are out at the telescope. So when the TEXES group comes out for a 10, 12 night run, that drops the percentage of remote observing appropriate by the appropriate amount. The pie charts show how the number of programs has expanded over the years. Back in the 1990s, before remote observing, usually it was one program per night. On occasions, there might be two programs, and very rarely were there more. By 2008, halfway through the growth period for remote observing, you can see that people were becoming more comfortable with splitting nights. So the number of programs that use the entire night fell significantly. And now we were scheduling in 2 and 3 programs. And now it is very typical to have 3 programs in a night, sometimes 4, and sometimes even more. So again, the scheduling can become very complicated. I love this map. This is one of the records that I've been keeping over the years. The red dots show all the locations around the world from which the IRTF has been used remotely, where the astronomers were actually operating the instrument, taking their data from those spots. One of the things that we do is to monitor productivity for the telescope by looking at the number of publications. So this right here is just a plot to show how the productivity has increased over the years. The breakdown of solar system objects you can see in the left-hand plot. In the right, that blue line that peaks up, leaving all the rest behind, is for specs. As I said, it really is the workhorse. It's it serves many different science goals. And so the other instruments are more specialized and generally are not scheduled as often and therefore do not produce as many publications. Dennis Crabtree keeps statistics for how the different observatories around the world do in terms of their publications and their citation rates and stuff. The plot that you see here, and we keep track of this every year. We get an update from Dennis, sort of showing how the different observatories are doing. We're interested, obviously, in where the IRTF falls, just to mainly for promoting the telescope and for funding. We want to make sure that the IRTF is pulling its weight in the science community. So this right here is a plot that shows for all publications across astrophysics and planetary science. And the IRTF in the red circle down there is not doing the greatest. It's sort of surrounded by other 4-meter class telescopes. It's a mix. The horizontal axis is the impact, the number of citations per paper that has been normalized. So normalized to something that Dennis uses. I think that it's the publications in AppJ or something like that, that he uses to normalize everything, so that if you publish in Icarus or some other journal, he can balance everything, normalize everything to the same scale.
Bobby, this is Mark.
Yeah.
Just a little question here is, what fraction of IRTF time is devoted to mission support? Because I would imagine that would be much less scientifically productive, if you will, when it's doing that kind of work.
Funny that you should ask that, because there is what happens if we pull out this. This was a question that we were asking, because obviously we thought that the IRTF was doing very well in terms of publications and citations and everything. But it just didn't feel right, because half of the time was going to planetary studies and mission support. So one of the things that I did was to pull out all of the planetary papers from all the different observatories and replotted this plot now, sort of on the same scale. So we have the mean impact per paper. And whoopsie, I need to go back. How do I go back? Here we go. The mean impact per paper is on the horizontal, and the total impact on the vertical axis. And here, so if we go back here, I just want to point out that HST is not even on this plot. HST would literally be up at a total impact of 5,000 or 6,000. So it doesn't even plot here. On this plot, HST actually is brought down into normal people's land. Up at the top, IRTF is doing very well. The papers per telescope, in terms of solar system papers, mission support papers, is high compared to other telescopes. And the impact actually in general is a lot better. Now, let me point out a straggler. Way over in the lower right-hand corner is WIN. Very high impact papers, but very few. It turns out that the telescopes like LBT, WIN, even CFHT go for the high science value targets. And in this case, WIN went after the interstellar objects, Oumuamua, and I forget the second one. Published a couple of papers and got a lot of bang for the buck, but that's why they are way over on the right-hand side of that plot. Another thing that we keep track of is PhD dissertations, where they come from. Here, by year, the solar system and astrophysics are separated out to sort of show you. Over time, it's been about 1/3 solar system, 2/3 astrophysics. That's generally the rule of thumb for publications, for IRTF, and for PhD theses. And then on the right-hand side, you can pick your favorite university. Arizona is in there. That combines LPL as well. I believe that combines LPL and Stewart, and 17 at the time of this count. Now, this is actually an old plot. It ends here at 2022. There actually is a newer plot that I just didn't have handy. The total count is now well over 300. It's up at around 330. Finding old PhD theses that, especially before the digital age, is really a challenge. And so I know that there are missing theses prior to about 2000. And just over time, I hope to stumble upon those and add them to the plot. Some science highlights. Jupiter here, one of the big things one of the big feathers in the IRTF's hat was monitoring the location on Jupiter for the Galileo probe entry. It was one of the few telescopes that could actually do it in real time. At the time of the entry, Jupiter was at a solar elongation of 9 degrees. Most telescopes don't like pointing there. If you look at the science article cover on the left, there's an inset way up in the upper left that looks sort of like I don't know, it looks like a white circular thing with a robot attached to it. That was a large plastic filter, I believe Mylar actually, that was placed over the primary mirror in order to shield direct sunlight, but to allow the thermal infrared to come through. And so that's how the IRTF was able to do that. Now, we don't use a filter like that except for very extreme cases like this. Normally, we're able to observe to solar elongations of about 17 or 18 degrees and higher. By the time you get that far away from the sun, observing is pretty simple. And again, all that we have to do is just protect the primary, make sure that the dome is used to shadow the primary. On the right, Glenn Orton has a long-running program of monitoring Jupiter in support of the Juno mission. Here's the different wavelengths. At 3.42 microns, you're seeing the Jovian aurora there in the H3 plus filter, and then the other wavelengths here. You'll see the size difference in Jupiter between the top row and the lower row. Top was near opposition, lower row near superior conjunction. For New Horizons, there was a long-running monitoring program of ices on Pluto that was carried out with SPECS, still is being carried out. And the data that was taken up through about 2012 was used in timing the New Horizons pass by Pluto in order to take advantage of a brighter ice region. The ice region, you can see that the plots here are plots of CO absorption on the top and nitrogen absorption on the bottom. They point over. The lower left is a grand sum plot that shows you where those particular bands are. The bands themselves are very small, typically, but with enough signal, you can dig them out. And so over time, over a rotation period, you can see that the strength of the CO and nitrogen absorptions changes. That corresponds actually to, the brightness there, that the brightest area in the center of those plots corresponds to a longitude of 180 degrees, opposite the side of Charon. That was known from HST images to be a bright spot, and so the IRTF confirmed that it was good ice absorption and therefore was targeted for New Horizons. Daytime observing, again, this is some work carried out by Mike Muma and Sarah Fagey. Daytime comets, whenever a bright one comes by, they get time to observe it, whether day or night. This happens to be 2020 F3 Neowise. I don't do comet spectroscopy very much, but I do know that the data that there's in this plot over on the left are three different orders, three different grading settings on iShell, showing the raw data and the telluric fit and the resulting species spectra for CO, H2O, and let's see what else is there, H2CO. Again, I don't do comet spectroscopy, but I see a lot of this, and I think that this is representative of the data that we can get from iShell for moderately bright comets. Now, I decided to stick this in because it's close to my heart. Asteroid spectroscopy, I was doing it as a grad student at visible wavelengths, came up, as Mark mentioned, with a taxonomy. That was then superseded by Francesca De Maio in 2009 with her paper that that linked the visible spectra and near IR spectra taken with SPECS. So over on the left-hand side, you can see some of the asteroid spectral classes, the S-types in the top, and the more unique types down below, the Rs and Vs. All of these are, they all contain the 1 and 2 micron silicate bands, but as you look at them, the shapes of the bands and the band positions do change a little bit. And that is sort of what the feature-based taxonomy is built around. On the right-hand side is the cheat sheet that Francesca drew up that shows the different classes and sort of a grand average of what the spectra look like. Now, IRTF does a lot of asteroid observations, most of it spectroscopy. There are tons of papers that have been published for asteroid spectra of NEOs and main belt objects. This right here just sort of gives you a flavor of what we can do. Now, there are some new things coming down the pike. New additions to the IRTF. Felix is a new acquisition guide camera that's replacing the old one that's been in there for since about 2000. We expect this new system to improve the telescope focus and image quality. It again uses another Andor camera. So once we found out that Morris worked, we're using Andor cameras now for everything. This system will include a small 2x2 Shack-Hartmann wavefront sensor that will be used to help monitor in real-time focus and collimation and make corrections in real time, hopefully improving the image quality and the science that we get out. The diagrams that you see here in the middle is just a layout of what Felix looks like. Up at the top is a pickoff mirror that moves around on an XY axis outside of the science field for the telescope. It's actually mounted up above where all the rest of the instruments are, sort of a gap in just below the mirror cell. And so it can move around in that area and see more of the field of view, more than what the instruments see. On the right shows a layout of sort of a U-shaped area. All the yellow area is the area that is accessible to this pickoff mirror. So hopefully when you set on a target, you can find an off-axis guide star outside in those yellow areas and use it for guiding and for image correction. Felix is actually going on the telescope right now. Another thing that's going on the telescope is an adaptive secondary mirror. This is an engineering project, not meant for science right now, but it's to test out a new technology for building deformable secondaries. In this case, it uses 36 actuators that will cover the area of that secondary that I showed you in an earlier picture. The project is being led by Mark Chun, who's an IFA astronomer interested in adaptive optics. The technology is developed by a Dutch company, and the work in designing this system is being done by a group from Santa Cruz and from the IRTF staff. So how does this get attached? Well, down in the lower right is an image of the old chopping secondary. The IRTF actually has two top-end rings. They would take in a crane, unbolt one ring, put on the other one, depending on which secondary mirror you wanted to use. Since the chopping secondary, the one that you see pictured there, is pretty much dead, we are replacing it with this adaptive secondary, at least temporarily, so that we can mount it onto the telescope and test it out during engineering runs. Now, the goal is, since the IRTF has a very small secondary, it means very few actuators are needed. The idea of this is to get onto the sky quickly with this technology and see how it works, and then step up. The next step would be building a larger secondary with more actuators for the UH 2.2 meter. And then ultimately, Keck, which has a 1.4 meter secondary, would have a very large number of actuators. So this is basically starting out on the technology and stepping upwards in a progressive manner, finding out what works, what doesn't, make corrections without just starting to build the biggest one first. Now, Spectre, we hope, is going to be another workhorse for the IRTF. This is still sort of a dream. Actually, it's more than a dream. Spectre is going to be a 0.4 to 4.2 micron IFU spectrograph, low resolution, meant to take spectra across that entire range in one shot. The field of view is small. It's only going to be 7 arc seconds, which is plenty for asteroid studies, for example, or for studying the satellites on the outer planets. The system consists of 3 channels, an optical channel, near IR, and mid IR that goes out to 5. The array goes out to 5.3 microns. The actual prism, the actual optics will only go out to 4.2 microns. You can see the layout in the diagram, the innards. The image slicer is mounted to the left wall. It's in the light blue there. That's where the light comes into, gets bounced, it divides it up into the image slices that then get passed around to 3 different prisms and arrays where it is dispersed. On the left-hand side, outside of the cryostat, is another and/or CCD, and it will provide a 3 arc-minute field for guiding and for acquisition. And so we're hoping that this gets started soon. This right here is a layout of how it works. You have a star on the sky. It goes through the image slicer, and it divides up the images into the slices that then get passed to the appropriate disperser. And then ultimately you restack those images in software, giving you a spectral image cube. The goals are, well, first of all, to give us simultaneous photometry, spectrophotometry across the very broad wavelength band to allow for absolute spectrophotometry, which is something that's very hard to do with a slit spectrograph where you lose so much light. Our hope is that on the IRTF, we will get a 1 magnitude gain in sensitivity over what specs can do right now in prism mode. And as you can see, the key science objectives are NEOs and small bodies, and for astrophysical infrared transients. Now, Spectre has completed a preliminary design review. It received a task order from NASA for 1.7 million to start construction. We did put in a proposal to NSF to help funding optical components, and particularly the image slicer, which is pretty expensive. The image slicer alone is probably about $750,000. But that proposal was turned down. So the plan right now is to continue using IRTF funds only and to build Spectre hopefully over the next 3-year period. On the right is a poster. This is actually where Spectre got its name from. Mike Connolly, who I mentioned at the beginning, the photographer, is also a huge Bond fan. And so this instrument needed a special name, and so he chose Spectre. And down at the bottom in fine print, you can see coming soon. I hope that that is the case. Moving forward, the staff of the IRTF, some of them have been around almost since the beginning. There were staff members who joined the IRTF in the early 80s, telescope operators, engineers, who have spent their entire career at IRTF, and they are now retiring. So there is a changeover in staff right now. Young ones are coming on and learning the ropes, and will hopefully bring new ideas. There is a new operations and maintenance contract for NASA from NASA that went into effect earlier this year. It extends through 2033 with an average cost of about $9 million per year. Now, it turns out that the 2033 year, that's a 9-year contract, 9.5 years. And that's a little unusual for NASA headquarters, but they decided to do that because it turns out 2033 is also the end of the master lease for Maunakea. So the big question is what happens next? Now, as I'm sure you're all aware, Maunakea went through some time of protests over the proposed construction of the 30-meter telescope project. The Maunakea land is ceded lands held in trust by the state, and it's managed by various agencies of the state. The Science Reserve is managed by the University of Hawaii and the Office of Maunakea Management. In 2022, the state legislature, in its infinite wisdom, decided to form a new entity to oversee the management of the mountain, called the Maunakea Stewardship and Oversight Authority. That committee has been put together, but there is a long learning process. They're just barely getting their feet on the ground. OMKM, the Office of Maunakea Management through the university, is still managing the land, but the idea is that OKSOA, the new authority, will take over in 2028. Now, in the meantime, any discussions about, because the new authority will have jurisdiction over any new lease agreements or management plan, any discussions about renewing the master lease for the mountain has been put on hold until 2028. And therefore, every telescope on the mountain is uncertain about what the future will hold in terms of whether or not astronomy will continue on the mountain and what the new lease agreements will look like. So time is short. everything needs to get done between 2028 and 2023, the end of the lease. If in fact the leases are not renewed, then telescopes on Maunakea will need to be taken down by 2023. Now, that process has already started a little bit. As part of the negotiations over TMT, it was decided that 5 telescopes on the mountain would be decommissioned before TMT goes in. 2 of them have already been decommissioned and removed. So this old picture of the mountain, you can take off the UH-Hilo Education Telescope way over on the left-hand side. That has now been just flat land. And the same thing is true with the Caltech submillimeter observatory, that sort of small golf ball sitting there in the valley below the optical telescopes. CSO was in operation for a long time on the summit. It ended operation in 2015. The dish was ultimately dismantled, removed, and has been shipped down to Chile and will be reassembled there for use there. But now the dome and everything for the CSO observatory on Maunakea is gone. Moving forward, farther, despite the uncertainties over the future of Maunakea, I think the IRTF staff and most astronomers associated with Maunakea have a positive outlook. For the IRTF, we want to continue to enable good scientific discovery, support spacecraft missions. Right now, our role in the Planetary Defense Coordination Office is a strong one, and we want to continue that. And close to my heart is to continue fostering the next generation of scientists. One of the unique things about IRTF, besides the daytime observing and everything else, is that we still encourage observers to come out to the summit. And that's actually rare for most of the telescopes on Maunakea that now are operated completely remotely. The IRTF still welcomes observers to come out to witness the thrill of observing at 14,000 feet and to learn where their data actually comes from. So that is something that will continue. And with that, I know I've gone long, but I'd like to thank you all.
Thank you, Bobby. Any questions for Bobby?
I have a question. Oh,
Go ahead, Dave.
I have a question. So you talked about, IRTF, and you have been there for a long time. Were you still able to use the telescope for your science projects? And if so, what were they?
At the beginning, yes, and it was asteroid spectroscopy. I was picking out not so much NEOs, but main belt objects, looking at doing spectral analyses, working actually with mineralogists. I have a very close connection with Jessica Sunshine at Maryland and Tim McCoy at the Smithsonian. We have sort of a little band of brothers going, where I would help with the observations and produce the data, and then they would do the fitting and help with the interpretations. And we did that for a number of years. But actually, to be honest, working at a telescope started taking more and more of my time. And actually, by about 2010, I was finding that it was a 24-hour-a-day job. I stepped up to take over as deputy director in 2016. And that just absorbed all of my time. Every time I thought that I had something finished, there was either an issue with an observer, a new observer who needed to be trained, something broke on the telescope and needed to be, dealt with. And then all of I call it paperwork, you know, keeping up all the metrics, the bibliography and stuff like that, and the telescope scheduling. I did essentially all of that. John Rayner, who's the director, we sort of split the tasks. I took care of sort of the day-to-day mulling around stuff. He took care of the hiring and firing and getting the money and going out and promoting the telescope at meetings and things like that. So he dealt with all the administrivia, and that left me to sit in my office and crunch and deal with observers. So that's a long answer, but to be perfectly honest, very little during the last 10, 12, 14 years at IRTF. And that, in fact, is one of the reasons that there was a number of reasons that sort of spurred me on to retirement. COVID opened up the eyes of both my wife and I in terms of the fact that life is probably not as long as I thought that it was going to be when I was in my 20s. And that there was things that we wanted to do, experiences that we wanted to have, not just sit on Hawaii working all the time. And hence the move to the mainland and trying to get away from the day-to-day operations of the telescope. I'm still closely tied to the IRTF. I still help them out with some of the bookwork and stuff, and I want to start doing that in a more official capacity. So in fact, one of the reasons for joining PSI is to be able to contract some of my time back to IRTF. But I'm also hoping to dig back into the science that I've been wanting to do for 2 decades now. And the things that interest me the most is colors and spectroscopy of family members, using them in order to understand, to better understand the extent of families, their formation, their mineralogy, things like that. So I'm hoping to get back into that more.
Thank you.
I'd say Bobby is now a neighbor of mine when I'm up in Portland. He's just across the river in Washington. So it's
That's
great.
right. Just have to swim across the river.
Yeah.
Hi, Bob. A quick question. The instrument OFI, yeah.
OPE, yes.
That can be used in conjunction with another IR imager, for example, right?
Yes.
Okay.
Yes. Yep. It's a totally separate telescope just hanging on the side of IRTF. And so while IRTF is observing, no matter what instrument you have in the beam on the IRTF, you can use OPE for whatever you want to. It's just that it's tied to the IRTF. So you're pointing to the same part of the sky that IRTF is in. So for example, for comet observations, let's say that you were doing comet spectroscopy, you could be doing broadband imaging at the same time.
Okay.
That's important for like flux calibrations and stuff, although the calibrations are in the visible. But, you know, in a lot of cases, brightening, you know, light curves, it's all tied together. So this is to give you sort of a visible wavelength monitoring of what it is that you're looking at for whatever science purpose, or just to know how the sky is doing.
What is the filter size there?
1/2 degree.
Not the field of view, the filter.
Oh, the filter.
Yeah.
That's a good question. I don't know. I don't know. I want to say that it's 2-inch, but I'm not absolutely sure.
Okay. But you can't have your own filter.
There is access to the filter port. We made sure that that was available. I think for, you know, if there was a special comet filter, for example, that you knew that everybody wanted to use, that there was a good scientific reason across the board for people to use, then I'm sure that it could be put in and left in. But it's not, I don't think that it's the case where they'll want to be changing filters routinely.
Okay. Thanks.
Yep.
Any other questions for Bobby? Yeah, well, thank you very much, Bobby.